Okay, welcome back here. We're going to, like I said, sort of just kind of continue reviewing. So hopefully it's helpful for you. Also, hopefully, this stuff does ring a bell as well. Seems like something you remember, I hope. All right, so again, since our final is obviously tomorrow, obviously we're done with pretty much all the labs and all that good stuff. A couple of reminders, kind of on that sense. Make sure obviously whatever needs to be turned in does get turned in. You have, I know for sure, the kinetics pre-lab needs to be turned in. I think I might need to put a spot for you to do that actually. So that will be up there shortly. And then also remember you do have the kind of take-home quiz that's also due tomorrow. So make sure that gets done as well, because again, it is worth points, hopefully some easy points, hopefully. So make sure that you do that. I don't know until the end. I'm probably going to do that sort of part at the end and stuff like that. So if you were here pretty regularly, pretty much you're probably okay on that in terms of that. So make sure you do get those stuff turned in. And tomorrow, like I said, the final will be around the same time as we normally take our exam. And again, the final will be pretty much the same sort of format. So there'll be probably a multiple choice part, and there'll also be a written part just like normal. You obviously need to use your proctorial like normal and all that good stuff. And like I think I may have mentioned yesterday, I'm not going to necessarily focus more on, say, one chapter versus the other. So I know we sort of finished up with kinetics, and so I'm not going to, necessarily focus all on kinetics and all that type of stuff or anything like that. So should be pretty well spread out overall. In terms of how many questions, honestly, I don't know, to be honest with you. I'm still sort of working on it, and I got until tomorrow, I suppose. But still sort of putting the finishing touches on it. So I would anticipate it might be maybe slightly longer than a normal exam, maybe not super much longer, but there might be a few more questions, obviously, since it covers a little bit wider of a range of chapters and stuff like that. In addition, there may be some questions that maybe multiple topics may come together, and that type of thing. So maybe slightly longer, but I wouldn't say super longer than maybe a normal exam, but it may be a few more questions. And honestly, at this point, I'm not 100% sure exactly what the total count will be. I'm still working on it, to be honest with you. Okay, so again, I think for tomorrow as well, I will have a lecture section. I'm probably not going to do much of anything, but just in case maybe you had some questions or something like that, it'll be like I'll be around, I guess. You could pop in if you want during lecture time and ask any type of questions and stuff like that. And then obviously you'll go and take the final and all that good stuff, and we'll be done. Yeah, it'll all be over with. That's pretty good. All right. So speaking of which, let us, I guess, kind of continue on. And again, just kind of going off the top of my head here. So let's see, we got to sort of drawing Lewis structures. Remember that, for the most part, things will obey sort of the octet rule. There is the exception to the octet rule that we talked about as well. And, there are some exceptions to that octet rule. And a couple of those exceptions that we talked about was, there's an incomplete octet. And that is somebody with less than 8 valence electrons. Guys that contain boron is usually, the guy that could kind of do that, or where that shows up. But really, in terms of sort of, there's also that odd number of electrons. So you could have sort of like those free radicals that have, one unpaired electron by itself. They're very reactive. But really, in this class and in most chemistry classes, the sort of exception to the octet rule that we talked about a lot is the expanded octet. And the expanded octet are those guys that can have more than 8 valence electrons. When you look on the periodic table It's right there where sulfur is, kind of to the left, to the right, and down in the nonmetal region. Those are the guys that really can that can kind of go over 8 valence electrons. And the reason they could do that is because really on the periodic table there, they are on period number 3, which means that's N equals 3. And on that third energy level, that's where we have S's, that's where we have P's, and that's really where we first start to see the d orbitals appear. And because they have those d orbitals available to them, even though they may not be using them, they have a place to kind of put the extra electrons in, and that's why they are able to go above 8. That's also why anybody on the period before that on the periodic table, like the N equals 2, like carbon, nitrogen, oxygen, and so forth, they can never go over 8 because they don't have the d orbitals available to them, because they only have s and p orbitals available to them. So when we get to sort of sulfur on the periodic table above and below, we can go above that, you know, for example, SF6, sulfur being 6 plus R 6 times 7. That's a lot math there, but I can go with 48. And again, sulfur is perfectly okay doing that. 1, 2, 3, 4, and 6, right? There we go. And again, we would basically fill in all the way around. And at this point, we obviously have way more there than 8 electrons around that sulfur. He's got 2, 4, 6, 8, 10 electrons. Not 10, 12. I learned to count. 2, 4, 6, 8, 10, 12 electrons around that sulfur. And again, he's perfectly okay with that. He can do that because he has those extra d orbitals to sort of house all those things. So out of sort of all the exceptions to the Octet rule, that's the one that, you know, we did come across the most, and it does come into play a lot. Again, second to that would be the incomplete octet, but mostly main people focus on the sort of expanded octet there. Now, another important thing in terms of bonding that we talked about when we were doing that was the idea of formal charge. And formal charge is the number of valence electrons in the atom by itself minus the number of non-bonding electrons minus 1/2 the number of bonding electrons. So for example, if we drew something like sulfate, right? SO4 2 minus. Again, that is 6 plus 4 times 6 plus 2, so that's 24, 26, 32. And you could draw a Lewis structure that looks something like this. And we could calculate the formal charge for everybody here. So for example, the oxygen on the outside has 6 valence electrons in oxygen minus 2, 4, 6 of the non-bonding electrons minus 1/2 of 2 for the bonding electrons there. And that 6 minus 6 is 0, minus 1/2 of 2, which is -1. So in this structure, the way it's drawn, the oxygens all the way around have -1 formal charge. If we do it for the sulfur in the middle, which basically looks something like that, sulfur has 6 minus 0 non-bonding minus 1/2 of 2, 4, 6, 8 That is 6 minus 4, which is a plus 2 in terms of the formal charge. And it has a plus 2 here. And if we add up everything, that's minus 4 on the outside, plus 2 on the inside. That is where, again, our minus 2 comes from in terms of the charge, instead of that charge difference. Now, we could use formal charge just like that, just to simply sort of calculate the charges on each of the atoms in those bonds. We also could use formal charge, as we talked about, to help us decide maybe a better structure from another one. A different structure you could have drew for sulfate was to double bond, do some double bonding there. And again here, the sulfate can do that because the sulfur in the middle is, there we go. The sulfur in the middle is has those d orbitals. And now if we do our formal charge for the guy on the right here, we have our oxygen, which is going to come out the same, 6 minus 6 minus 1 half 2, minus 1. So again, this guy here is minus 1. This guy here is minus 1. The double bonded oxygen would be 6 minus 4 non-bonding electrons, minus 1 half of 4. So that 6 minus 4 is 2, minus 2 is 0. So formal charge here is 0. Formal charge on this guy would also be 0. And if we did our sulfur, which looks something like this, that's 6 minus 0 minus 1 half of 2, 4, 6, 8, 10, 12. Gives me 6 minus 6, which is 0 as well. So they both are sort of acceptable structures, Lewis structures for sulfate. But by using formal charge, we would determine that this guy in this situation would actually be the better structure based on formal charge. Here we have 0 formal charge on the oxygens. We also have 0 formal charge on the sulfur. And remember that when we're sort of trying to decide, what's the best situation for formal charges, a situation where we have all zeros is sort of your best. A situation where if we have equal charges in terms of numbers, the more negative formal charge is on the more electronegative atoms. So those are some rules that you could kind of follow to help you. But here we also brought down the formal charge on the sulfur from plus 2, which is a high positive charge, down to 0. And remember, structures with positive 2s, positive 3s, really high sort of positive charges are less likely to be the best structure than ones where you could kind of get everybody down or close to 0, keeping those negative formal charges on the more electronegative atom. Like in this case on the oxygen, we have our more negative formal charge on the guy on the right, while we minimize all the positive formal charges on the sulfur and all that. So again, that was an important topic that we talked about, that we can, again, use formal charge to help us decide between different structures. Also could help us decide, should we double bond in a situation? If we can, should we triple bond in a situation? If we can, we could use formal charge to help us decide that. We then are talking about geometry, and really 2 types of geometry. We had electron pair geometry, and we also had molecular geometry. And remember that when we do geometry, we basically treat double bonds and triple bonds as 1 electron pair and 1 bond. So only when you're doing geometry, which is Vesper, we do that 1 electron pair, 1 bond for double, triple bonds, doesn't matter. They're only counted as that. When we do geometry, the easiest ones to do geometry on are diatomic molecules. So something like F2, H2, HF, whatever it may be, O2. All these guys here, because they're diatomic in terms of geometry, they're all going to always be linear, because it's really only 2 things. You can only place them on opposite ends, basically of a straight line, and they will always have that linear. It's when we get into our sort of 3 or more atoms involved, that we have to look at electron pairs and number of bonds. And when we do that, let's kind of make my table backwards here, I guess. We'll go this way. So we had sort of a chart, and we can do it by looking at really the number of electron pairs and the number of bonds. And really, you know, this is sort of the easiest way to sort of do that. If we had something like 2 electron pairs and 2 bonds, that's going to be linear and linear for both of those. One describes the electron pairs around the central atom. The molecular geometry decides the overall sort of shape of it. And again, this would be something like this. If we move to sort of something where we added another on there, 3 electron pairs and 3 bonds, that is what's known as trigonal planar, and also trigonal planar. Also sometimes referred to as triangular, depending on the situation. We also could have 4 electron pairs and 4 bonds, and that would kind of fill this up. And that is what is known as tetrahedral and tetrahedral. You could also have 5 electron pairs and 5 bonds. This is getting into our expanded octet in this case, and that is trigonal bipyramidal and trigonal bipyramidal. Now, we also have 6 electron pairs and 6 bonds, which is octahedral. Again, this is going to also be our expanded octet. But what we see in each of these cases is when we have no non-bonding electrons or no lone pairs on the central atom, both of these names are pretty much the same. And the reason for that is we basically have only one type of electron interaction happening. These are all bonding electrons. So we have just bonding electrons happening there. And bonding electrons are sort of the, I want to say the safest, but the best in terms of being near each other. Because the whole idea of this, right, is we have electrons near electrons, and they definitely don't want to be near each other in that case because they're both negatively charged. So that's why we can sort of have these guys where it doesn't really affect the overall shape. But once we start introducing non-bonding electrons into the mix, we have the non-bonding electrons near bonding electrons, which is not great. And really sometimes the worst case scenario where we get non-bonding near non-bonding electrons, they really don't want to be near each other. So, you know, we saw some instances of that, and the name that changes is actually the molecular geometry name is actually the one that changes. And for example, if we had, let's see here, 3 electron pairs and 2 bonds, 3 electron pairs would still be trigonal planar, but it will then become something that's known as angular. So something like, again here, 1, 2, 3 electron pairs and 2 bonds basically happening. We also have 4 electron pairs and 3 bonds. 4 electron pairs still going to be tetrahedral. But again, because that non-bonding electrons are there, we end up getting trigonal pyramid. We also had 4 electron pairs and 2 bonds, like in water, for example. And that also is tetrahedral in terms of the geometry name, but this becomes bent or V-shaped. The question is for this one, and could you call it bent, or do you want to call it angular? I probably prefer angular. I probably won't mark it wrong if you call them bent. Most people will do angular bent or bent angular, something like that. Because the real reason is, as we talked about when we, I think, went through it as well, there is really a difference in terms of the bond angle. The bond angle for this guy here that's angular is just under 120. The bond angle for the bent or V shape is like, 104 or something like that, depending on which one you're talking about. So there is a slight difference in that bond angle, but for our purposes, you probably go either way. But if you can, maybe stick with the angular for that one and the bent or V shape for this one. That way, again, you have sort of that distinction between them. We also got into, remember now, our expanded octets. We do have our 5 and our 4 bonds. So 5 electron pairs and 4 bonds. Since it still has 5 electron pairs, that's going to be our trigonal bipyramidal. Again, the electron pair geometry doesn't change, but that will give us a shape that's known as seesaw. I can spell that, seesaw. Our distorted tetrahedral in some books. We also had, I think, a 5 and a 3 sort of combination. Again, also going to be trigonal bipyramidal. But again, that's going to give us that T shape that we saw. We had a 5 and a 2 situation as well. And that is going to give us our still, I'll just quote it here, same name there for our electron pair, but that's going to end up being linear as well. And then we obviously have the 6 ones. So 6 and 5 and 6 and 4. Let me just go, I guess, next slide here. I'll just kind of continue this way. We had 6 electron pairs and 5 bonds. Again, the 6 electron pairs is going to be octahedral for the electron pair geometry. And again, in that sort of 6 and 5 situation, you have square pyramidal. Borrow that, square pyramidal. And again here, this is the molecular geometry. 6 and 4 gives you octahedral and your square planar. So these were the geometries, and again, sort of the best way to do it, as we talked about, is to sort of draw, a good Lewis structure, and then basically count up how many electron pairs and how many bonds. And again, really the idea there is double bonds, triple bonds, 1 electron pair and 1 bond when you're doing that. Now, we also talked about with that, the idea of molecular polarity. And molecular polarity, again, is different than bond polarity. And it has to do with really, when you have diatomic molecules, it's pretty easy. Diatomic molecules, as we talked about, this has 1 bond and it's a polar bond, which means this would be a polar molecule. If you have a diatomic molecule where you have a nonpolar bond, again, because it's the only bond that's there, it'd also be a nonpolar molecule. So diatomic is pretty easy to figure out molecular polarity. When you have 3 or more atoms, you have to look at, are there polar bonds? And you also have to look at the molecular geometry as well. And again, the classic example that we did is if you took something like carbon dioxide, it does have polar bonds heading to the oxygens being more electronegative. Now, when we look at this, it has 2 electron pairs and 2 bonds. The geometry of this is linear, as we talked about. So essentially, as we talked about, we have an oxygen pulling one way, we have the oxygen pulling the other way. They are going to cancel each other out. So although this does have polar bonds, the geometry here makes them actually cancel out. These little dipole arrows are vectors, which means in some cases they could add to each other, in other cases they may not. And in this case, they actually do cancel out, and this would be a nonpolar molecule because of that. So anywhere where those dipoles head in equal and opposite directions, they will cancel out. Anywhere where they sort of head towards each other, they will also cancel out. But when they're pulling unequally, like for example, in the case of water, also has polar bonds heading towards the oxygen. But in this case, I was trying to draw it up here. They basically add to each other in this particular case, and we get a net dipole moment happening here, right? Dipole moment. And that means overall, the oxygen side of water is more negative. The hydrogen side is more positive. There's an overall separation. So sometimes it's hard to sort of visualize this. So we talked about the idea of symmetrical geometries and unsymmetrical geometries. So really, we could look here. These guys here that have no non-bonding electrons, except for linear. We'll leave linear off of that. But these guys here that have no non-bonding electrons from about there and down, if everything attached there is the same, and it's one of these geometries where essentially you draw it and you have no dots on the central atom, it will be a nonpolar molecule like we talked about. Those are symmetrical geometries. If you replace one of those things in that symmetrical geometry on the outside with something different, it typically will go from nonpolar to polar. But everything on the outside the same. It's one of these symmetrical geometries going to be nonpolar. And everybody that has dots on the central atom, if they are essentially the same atoms attached on the outside, will be polar in most cases. So you see dots, everything is the same, probably going to be polar in terms of molecular geometry. No dots, everything the same, going to probably be nonpolar. There isn't two exceptions to the ones with dots where it can be nonpolar, and that is this linear here, the 5 and 2 linear. If you have everything the same and it's that, it's going to be nonpolar, again, because it's basically linear, so it's a straight line. The other exception would be this guy as well, the square planar. If you have everything attached is the same on the outside, even though you have some dots there, it will be nonpolar as well. So that's sort of the easier way to remember polar, nonpolar, molecular polarity. Again, probably 9 times out of 10, draw that Lewis structure, no dots on the central atom, everything the same, nonpolar. No dots on the central atom, different atoms, polar. Dots on the central atom, everything the same, going to be polar as well. So those are sort of the quick way, almost 90%, 95% foolproof there that you probably will get the right answer. Again, like anything else, there's exceptions, but you probably will get the right answer. Now, when we talked about this as well, we went into sort of another idea of bonding, which is known as hybridization, right? And hybridization is when we take those atomic orbitals like S's, P's, and D's, these are what are known as atomic orbitals, and we basically mix them together and make what are referred to as hybrid orbitals. Hybrid orbitals, the idea and sort of the benefit of it is that we create a bunch of orbitals that are all the same shape, they're all the same energy, so when they go to bond, they're able to bond a little bit better with each other, and it also accounts for the bond angles that we see in molecules. Now, when we mix them, the easy way to do it or to remember it is, as we talked about, you know, it's kind of like there's an s orbital, right? And there are 3 p orbitals and there are 5 d orbitals. And when we do this, this is related to basically electron pair geometry. So if you remember our electron pair geometry, we had linear, we had trigonal planar, we had tetrahedral, we had trigonal bipyramidal, and we had octahedral. And essentially, in terms of electron pairs, this was 2 electron pairs, 3 electron pairs, 4 electron pairs, 5 electron pairs, 6 electron pairs. So when you are trying to figure out hybridization, for example, something like this, something like this, something like this, and so forth. You basically go through and count it just like you would as you were doing electron pair geometry, VSEPR, basically molecular geometry. Double bonds, double bonds, triple bonds count as 1 electron pair. So essentially, if we look here, this is around the central atom carbon, 1, 2, 3, 4 electron pairs, which means if we look at it, we start at the bottom, 1, 2, 3, and 4. I combined 1s and 3 p's, and that's 4 electron pairs. So the hybridization here would be sp3. I come over here, there's 2 electron pairs, S and a P would give me 2, S and P. 3 electron pairs, an S and 2 P's, sp2. 4 electron pairs like I just did, 1, 2, 3, 4 gives me sp3. 5 electron pairs, 1, 2, 3, 4, and up to the D now. That gives me sp3d. And lastly, 6, 1, 2, 3, 4, 5, and 6 gives me sp3d2. So that's sort of the easy way to do it. Literally just count, and you could just start with the letters and kind of work your way up there. So over here, if we look here, we have 1, 2, 3, 4 electron pairs, even though they're not all bonding. So 4 electron pairs means this guy here was sp3, so would the nitrogen here be sp3. Carbon here, 1, 2, 3 electron pairs. 3 electron pairs, this carbon here would be sp2. This carbon here, and the triple bond, 1 and 2 electron pairs would be sp, and so would actually this carbon here be sp as well. So to assign hybridization, it's pretty simple to do. You can almost just draw this and just, put dots as you count. Always start at the S and work your way up. And basically you can figure out the hybridization doing it that way. It's relatively easy in that sense. And with this stuff, we also talked about sigma bonds and pi bonds. And remember that basically any single bond that you have is a sigma bond. And really what sigma means is the orbitals are going to head onto each other. So they're going to run right into each other and create that overlapping area. When you have a double bond, the first bond is the sigma bond, and the second bond is a pi bond. The pi bond is the sideways overlap of unhybridized p orbitals. While again, our sigma bond really is just our guys coming straight onto each other and head on. Our triple bond, 3 lines, 1 is a sigma bond and is made up of 2 pi bonds in that case. So 1 sigma and 2 pi bonds. So that will allow us to just very simply, without really having to figure out too much going on, for example, if we looked at something like this, it would have 1 sigma bond there, 2 sigma bonds, 3 sigma bonds, 4 sigma bonds, 5 sigma bonds here. In terms of pi bonds, that would be a pi bond, that would be a pi bond, and that would be a pi bond, and it would be 3 pi bonds in this particular case. And again, you could do the hybridization. This guy has 2, would be sp. This guy has 2, would be sp. This guy has 3, which would be sp2. Believe it or not, this guy here, you could also do 1, 2, and 3, which would be sp2, which would be the oxygen. So again, you could very quickly sort of identify those things without having to really draw too much by, again, kind of keeping it simple and counting. All right, so I think that was mostly everything in terms of bonding. We didn't talk about molecular orbital theory, so obviously you still don't have to worry about any of that as well. We then got into talking about, let's see here, atomic mass, which again is that number that we find on the bottom there of the periodic table is our atomic mass. And remember that the atomic mass really is the average atomic mass of all the naturally occurring isotopes. And they picked a standard, which was the carbon-12 standard, to compare everybody to. Carbon-12 had a mass of exactly 12 AMU. And that allowed you to compare sort of the mass of everybody, sort of how massive it is in comparison. And to actually calculate the atomic mass, we can take the percent abundance of one isotope times the atomic mass of that isotope, plus the percent abundance of the second isotope times the atomic mass of it. And you could kind of continue that through. And that'll give you the atomic mass that you find on the periodic table in AMU, which is atomic mass unit. Remember that what we see there and there is that average atomic mass of all the naturally occurring isotopes. So for example, carbon-12, say, is 98% occurring. Carbon-13 is like 1% occurring. You would take the 98% for the carbon-12, convert it into a decimal, times it by the molar mass of carbon-12, and then added to 1% converted into, or 1.8% converted into a decimal, and times it by the atomic mass of the carbon-13 isotope and add them together. And that's essentially how we get those numbers on the periodic table. Now, as we talked about, what we typically, though, use those numbers for, like for carbon, 12.01, is we usually use it as the molar mass. And the molar mass is grams per mole. And it essentially is our conversion factor to do just that, go from grams to moles, or moles to grams. And we use the molar mass. So for carbon, for example, the molar mass would be 12.01 grams per mole. And you can use it as a conversion factor. You can use it as 12.01 grams over a mole, or a mole is 12.01 grams. And again, we could use the molar mass to convert from grams to moles, which is a very important sort of conversion. As we've seen this semester, you need to use moles in a lot of calculations and go backwards from moles back to grams. You could do that for an individual element like carbon. You could do that for something like water. You would just add up all of the parts. So 2 times 1.008 from the periodic table for hydrogen, plus 16 for our oxygen, gets you something like 18.01 grams per mole, and you could use that. We also saw about Avogadro's number. Avogadro's number is 6.022 times 10 to the 23. And the units here could be particles, could be atoms, could be molecules, and that equals 1 mole of something. And really we use Avogadro's number to do that conversion, go from atoms or molecules to moles, or backwards, moles to atoms or molecules. And again, same idea. We could use it as a conversion factor. Or we could do it opposite there. A mole is 6.022 times 10 to the 23 atoms. So that is our sort of conversion factor to do that, to go one way or the other. Remember that we only want to use Avogadro's number when something is mentioned about atoms, molecules, particles. We don't want to use it if there's no mention of that. So we also talked about percent composition. So for example, if we had CH4, we could figure out the percentage of carbon and the percentage of hydrogen that's in there by basically getting the molar mass of this guy. The molar mass of this guy would be 12.01 for our carbon, our 4 times 1.008 for our hydrogen. That gets us 12.01 plus 4 times 1.08. Something like 1604 grams per mole. And if we wanted the percentage of carbon, we would take how much carbon is in that one formula, which is 1. We would divide it by the 1604, times it by 100. Gives us like 74.9% carbon. We could subtract from 100 at this point, or we could do the same calculation there for our hydrogen, which there are 4 of them, divided by the mass times 100. And that gives us something like 25.1% hydrogen. So we can figure out really the percentage by mass of each of the elements that are involved there by using the formula to do so. And that led us into sort of our discussion of 2 types of formulas, and that is the empirical formula and the molecular formula. And remember that the empirical formula is the simplest whole number ratio that's present, while the molecular formula tells us exactly how much is present of each of the atoms that are present. So for example, if the molecular formula is C2H4, that is a 2 to 4 relationship, which is the same as a 1 to 2 relationship. So that would be your empirical formula on the left and your molecular formula on the right. Now, to calculate the empirical formula, you basically need to take the percentages. If they give it to you, convert it to grams, then convert the grams to moles of each element. You then need to divide by the smallest number of moles. And if you do that and get all whole numbers, that would be your empirical formula. So again, if we converted, say, we had 6 moles of A and 2 moles of B when we did this, we would divide everybody by 2, which is the smallest number of moles. That would give us 3 for the A and 1 for the B, which means our empirical formula would be A3B. Again, if you don't get a whole number when you do that, you do need to multiply by a common number to get you there. So for example, say you divided instead of 1 and 3, you got like 1.33. That's too far away to round, so you need to multiply that by 3, for example, which would give you 3.99, which is about 4. So you would then take the formula you got and multiply everybody by 3, and that will give you your correct empirical formula. So remember, you can only really round if it's really close to that whole number, but if you got something like 0.25, 0.33, something like that, that's too far away basically to round. The molecular formula you could calculate by basically, you need really 3 things. You need the empirical formula, you need the molar mass of the empirical formula, and you also need the molar mass of the compound. And this number is usually given to you in the problem. The other 2 you may have to actually calculate like we just talked about. But once you get both of those things, you take the molar mass of the compound that's given to you. You divide it by the molar mass of the empirical formula, and that will give you a number. So for example, let's say that number was 4. You would take that number and multiply your empirical formula by, so let's say that was our empirical formula from last time. We would multiply this whole thing by 4, and that would give us A12, B4 as our molecular formula in that case, if this was our empirical formula. Okay, so let's see. Then we perhaps talked about nomenclature. We talked about naming. And we talked about some different types of naming. We started really with ionic naming. And that is type 1, which is a metal and non-metal. And here the metal is the important part. It is group 1, 2, 3, silver, silver, cadmium, or zinc. And what they all share in common is they have fixed charges, those metals, which means we use the whole name of the metal. And the non-metal, we drop the last part of the name and we add that IDE to it. And that's not to be confused with type 2, which is also a metal and non-metal. And here again, the metal is also the important part there. It is typically a transition metal. Or just to the right, underneath the staircase on the periodic table to the right there, where we have lead, tin, antimony, those guys. And because they have their transition metals, they have a variety of charges or variable type charges. So we basically name it the same way. The only difference is we need to take the whole name of the metal, and we do need to add that Roman numeral here. And the non-metal will still get the IDE at the end of it. But the Roman numeral, again, where people mess up on, as we've talked about many times, is not how many metals you have, but is actually the positive charge on the metal. So if you took out one of the metals by themselves, you know what that positive charge would be. So an example here would be something like sodium chloride would be NaCl. Something over here would be like FeCl2. This would be iron Roman numeral 2 chloride. Also, we talked about in the metal, non-metal sort of naming, even if you have more of, say, like we do there, the Cl2, we don't affect a name. We don't do any prefix on it or anything like that. Remember as well, when we have an ionic compound, all the positives and all the negatives, when you put it together for a formula, need to equal 0, right? And that's why here, the iron has a +2 charge, our Cl has a -1 charge, so we need 2 of them to balance out that +2 charge that's there, as opposed to over here where sodium's group 1 has a +1 charge, chloride is group 7, a -1 charge, so one of each of those will get you to 0, and it would be balanced. We also talked about type 3 nomenclature, and that is actually covalent compounds or molecular compounds. Covalent bonding, basically, this is 2 nonmetals. And this is actually where we do use prefixes. People want to use it everywhere else besides here, but this is where we use those prefixes like mono, di, tri, tetra, penta, etc. And remember a couple of things with this. We do not use mono on the first name, but we use it on the second. We also will get sometimes some vowels that will back up, like a O and an A, where we typically drop the O. 2 O's, we drop the O, an A and an O, I think is the other one I was thinking about. We kind of dropped the A and stuff like that. So instead of like CO being carbon monoxide, this is carbon monoxide, 1O in that particular case. So these are the easiest ones to sort of name and do the formula, because pretty much you just pick the prefix and you kind of write it correctly using the right prefix. And if you're given the name, like dinitrogen trioxide, as I just make it up. When we see the prefixes, we don't have to worry about balancing anything. So di is 2, nitrogen is N, tri is 3, oxygen is oxide. And you could just write the formula really quickly. Nothing has to be balanced in terms of these guys. So they're relatively easy in that sense out of all of them. We also then talked about polyatomic ions. Polyatomic ions are those groups of nonmetals that have sort of special names and charges, like NO3 minus is the nitrate ion. NO2 minus is the nitrite ion, ITE. And that's usually the pattern that you see when you're dealing with a group of 2. The one with more oxygens ends in 8. The one with the least number of oxygens ends with 8. In a group of 4, like ClO4 minus, ClO3 minus, ClO2 minus, ClO minus, we also add something to those names. So the ones with the most oxygens starts with per, ends with 8. This would just be chlorate. This would be chlorite. And this would be hypo, the one with the least number of oxygens, chlorite. So again, the 2 that have this least number of oxygens ends with 8, 2 with the more oxygens ends with 8, but we do put per on the one with the most in a group of 4 and hypo on the one with the least. We also do some things like HCO3 minus. This is hydrogen carbonate, because we basically put a hydrogen in front of it, carbonate, or this is sometimes referred to as bicarbonate as well. Now, how we name these guys is because a majority of all of the polyatomic ions are negative, except for this guy, which is the ammonium ion. Most of them are negative, which means if they get hooked up with a metal, we follow kind of type 1, type 2 rules. So if we had something like NaNO3, this would be sodium nitrate. Again, no need for Roman numeral because the sodium is group 1, always going to be positive 1. Although if we hook it up with CuNO3, this would be copper Roman numeral 1 nitrate. And same idea here, nitrate is -1. That means the copper here has to be +1. And because copper is a transition metal, could be +1 or +2, we do need to specify that in this case, it is the +1 we're looking at. That also led us into another type of naming, which dealt with acids. And acids are really guys that can produce H+ ions in solution. And to name acids, it really all is about oxygen. And if the answer is no to oxygen, you basically start the acid with hydro something ic acid. So HCl. We typically put the aqueous symbol next to it to imply that it's dissolved in water, that it's an acid, as opposed to if we had just HCl that's a gas, that would be hydrogen chloride gas. This would be hydrochloric acid, again, because of the aqueous symbol that is present. If it does have oxygen, yes, it will basically have one of those polyatomic ions that ends in ate or ite. And if your polyatomic ion ends in ate, your acid name will be something ic acid, like we saw there, HNO3. NO3 is nitrate. This becomes nitric acid. If your polyatomic ion ends in ite, it is something OUS acid. So we'll just do his partner there. NO2 is nitrite. This becomes nitrous acid. So again, also on this one, there's no mixing. So no hydro is only for ones that do not have oxygen involved. And again, no hydro on the ones that do have oxygen involved when you name it. Okay, so then we talked about some stuff. We talked about equations and balancing equations. And obviously when we balance equations, it is the coefficients that we change, and only the coefficients. So if we had N2 plus H2 goes to NH3, if we want to balance this again, we talked about making a table is sometimes helpful. You got 2 on the left and 2 on the left for that, 1 and 3. So we could start with the nitrogen by putting a 2 in front. That gives us 2 nitrogens and 6 hydrogens. And to fix that, we could go to the other side there and put a 3 there, which would give us 6. And again, this would represent a balanced equation. We always want to use balanced equations whenever we are using an equation or using it for calculations. Always should be balanced. That's basically sort of the approach, right? Is sort of put the coefficients in. A lot of times people do trial and error. We also talked about the idea that if you do have a lot of polyatomic ions involved in an equation, sometimes it's easier to keep them together and sort of balance them as whole units rather than going sort of element by element and table like that. We also talked about types of reactions. And we really sort of broke it up into sort of 2 big categories. We had our double displacement reactions. And we also had our redox reactions, right? So those were sort of the 2 major sort of categories for classifying reactions. And as we talked about as well, you can classify the same reaction in many different ways depending on sort of what you're looking at or trying to maybe focus in on. So under sort of that big umbrella of double displacement reactions, which in general have a sort of formula of A and B plus C and D, where the way you could recognize that this is a double displacement reaction is they are both ionic compounds. So you have a positive guy, a negative guy, a positive guy, and a negative guy. And basically what happens is these 2 guys will switch partners, right? And we will get A and D coming together to make a new ionic compound. And we'll get C and B come together to also make a new ionic compound. Now, some of these guys will result in a solid being formed, and that is what is sometimes referred to as a precipitation reaction. So for example, if we take some silver nitrate plus some sodium chloride, and again, positive, negative guy tells us this is going to be a double displacement reaction. These guys are going to switch partners, and the silver, which is positive 1, will come together with the chloride, which is negative 1, and that actually will make a solid. The sodium will come together with +1 with the nitrate, and that will make aqueous. And this is a precipitation reaction because we made silver chloride, which is a precipitate. We also talked about how you know that, you know, the silver chloride is going to be the solid. And for that, if you remember, we use our solubility rules, which just a couple of them. Nitrates are pretty much soluble in everything. Chloride also soluble in everything except for 3 things: silver, lead, and mercury 1. And because in this case the silver came with the chloride, that's why it's insoluble. And if you use those solubility rules and something is soluble, it gets that aqueous symbol. And if something's insoluble, it gets that solid symbol, using that table to help you out. Now, this type of reaction, which is again classified really as a double displacement reaction, can be classified also as a precipitation reaction. The way it's written here is what is known as the molecular formula. But we also talked about the idea that you could write another formula where it really does describe what's happening in the solution. And when things are aqueous, they typically are strong electrolytes and 100% break apart. And for example, the silver nitrate would break apart into the silver ion plus the nitrate ion. The sodium chloride would break apart into the sodium ion and the chloride ion. Now, when you do this type of equation, anything that's solid, liquid, or a gas stays together, or if it's a weak electrolyte, will also stay together. And the silver chloride, because it's a solid, would stay together, and we would get our sodium ion and our nitrate. And this is what is known as the total ionic equation, our complete ionic equation. And when we look at this equation, we typically can find on both sides some ions that look exactly the same. And in this particular case, the nitrate and the sodium here are our spectator ions. And spectator ions, like we talked about, are really just guys hanging out there to balance out the charge. They're just watching what's going on. They're not really involved in the product being formed, and typically we get rid of them. And what we're left with is the third type of equation we talked about, which is the silver plus the chloride coming together in this example to make silver chloride. And this is what is known as the net ionic equation. So molecular equation, total ionic equation, net ionic equation are ways that we could kind of describe really, you know, we could do net ionic equation for anything really, but a lot of times it's used here for double displacement reactions. And here, this really does show you the actual reaction that's happening. So when you mix that silver nitrate together with that sodium chloride, it is really this silver ion from the silver nitrate and the chloride ion coming together to make that white solid that we typically would see. Again, strong electrolytes are things, as we talked about, which 100% break apart into ions, conduct electricity very well, so a light bulb shines very brightly. Weak electrolytes mainly stay together, but do break apart a little bit into some ions and does conduct electricity, but nowhere near a strong electrolyte. And that's why weak electrolytes typically we do keep together when we do total ionic or net ionic equations, and we don't break them apart. And the last one is a non-electrolyte, which will dissolve, but will not produce any ions. And because it doesn't produce ions, it doesn't conduct electricity, and again, considered a non-electrolyte in that case. Another sort of reaction that we talked about that sort of falls under that umbrella of double displacement was acid-base reactions or acid-base neutralization reactions. And basically, when you react an acid plus a base, you typically get two things. You get a salt and water. The water basically comes from the H plus from the acid and the OH minus from the base. This is essentially where you get that water from. And in this case, if we took hydrochloric acid and reacted it with sodium hydroxide, again, it really is a double displacement reaction because that's positive, negative, that's positive, negative. Again, the H plus is going to go with the OH minus to make our water, and the sodium and the chlorine will come together to make our sodium chloride. And again, this is an acid-base neutralization reaction. It's really called that because if we do take it to our total ionic equation, and we find our spectator ions here, which is chloride and sodium in this case, and cancel them out. Our net ionic equation that you get whenever you mix a strong acid with a strong base together, doesn't matter the combination, is this. It's basically the H plus and the OH minus coming together to form water. Hence why it's called an acid-base neutralization reaction, because essentially it formed water. And that's essentially what you get here. So again, acid-base neutralization reactions are a lot of times double displacement reactions, but they are sometimes classified as acid-base neutralization reactions instead of double displacement reactions. So double displacement reactions can be precipitation reactions. They could be acid-base reactions. We also had gas-producing ones, if you remember. So for example, if we had HCl and some sodium carbonate. Again, positive, negative, positive, negative. When they swap around, we will end up with H2CO3 plus some sodium chloride and maybe a little balancing here to make everything all legit. So we got 2, 2, I think. We got CO3 and all that. But this is a double displacement reaction, which they exchange. And if you remember, sometimes in these reactions, something like this, which is carbonic acid, will actually then go through a decomposition reaction very quickly and will produce CO2 gas and water. And so we saw some gas-producing reactions, which were double displacement reactions as well, also occur. Now, sort of the other sort of big umbrella of classification was redox reactions. And redox reactions are oxidation and reduction. And remember that oxidation means basically that it loses electrons, right? Reduction means that it gains electrons. And remember, you could do the oil rig to remember that. The Leo the lion goes grr as well, as ways to remember that. We also talked about sort of oxidizing agents and reducing agents as well. The oxidizing agent is the guy that gets reduced, while the reducing agent is the guy that gets oxidized. And that's because, as we talked about, they cause that effect in the other guy. And these type of reactions can be a variety of different reactions, but a very common one is a single replacement reaction. And in a single replacement reaction, we have A plus B, C. And the way you recognize this, let's say ionic compound, and this A could be a metal or non-metal. So for example, what happens is this guy will come and kick out if he's a metal, and we will get AC plus B by itself, a new ionic compound. Again, this guy has no charge. So if we took some, say some zinc plus some hydrochloric acid, again, positive, negative. This guy has no charge at this moment. He comes in, he kicks out that, and we get some zinc chloride and some hydrogen gas that is produced in this reaction. Also do a little bit of balancing there to balance out everything. This is a single replacement reaction. This is also a redox reaction because, as we talked about in terms of oxidation states or numbers, you could assign oxidation states to what's going on here. And for example, anything in a standard state that's uncombined will have an oxidation state of 0. So zinc here by itself, uncombined, has an oxidation state of 0. The hydrogen here has an oxidation state of +1. The chlorine here is -1. When we go to the other side here, our zinc actually does have a charge in this case. It becomes +2. Chlorine is -1, and the hydrogen now is by itself. So if you remember, we talked about you could use a number line to help you decide what is happening. And if you become more positive, you are going through oxidation. And if you become more negative, you are going through reduction. So what we see here is the zinc is actually going from 0 to +2 on this side. So it's going from 0 to +2. It's going through oxidation, which means it's giving off a couple of electrons, right? Oxidation. Well, if we look at the H here, the two H pluses, that is +1 on this side, to H2 on this side, which is 0, it is going from +1, which is to the right here, towards 0, going to the left, which means it's going through reduction. So it actually is gaining 2 electrons, right? And this way I wrote it here, this is what is referred to as the half reaction, the oxidation half reaction. This is the reduction half reaction in this case. And if you take both of those half reactions, and you add them together, and before you can add them together, as we talked about, the one thing you need to make sure of, right, is that the electrons are the same in each half reaction. When you do that, you actually do get a net ionic equation for this reaction, which looks something like this, which shows that really what's happening in this reaction is our zinc is going from a 0 to a +2 oxidation state, losing 2 electrons. Those 2 electrons are then picked up by the H+, and it gets reduced in this particular case. So this is a way you can actually do a net ionic equation for a redox reaction as well. And that would be this equation here. We also talked about, really balancing full redox ones in acidic or basic solution. And when you want to balance those guys in either acidic or basic conditions, more complicated redox ones, that's the ones where you need to split into your half reactions, your oxidation reduction. You need to balance all elements besides oxygen and hydrogen. And then remember, this is where we add our water, and we add the water to balance the oxygen in each half reaction. And for every water that we add, we need to add 2 H pluses to the other side. And again, the purpose of adding the 2 H pluses to the other side is for every water you add to one side that needs the oxygen, you are also adding 2 hydrogens along with it. So you need to balance out the hydrogens on the other side, otherwise you will be off. We then would add electrons to balance each half reaction. Make sure the electrons are the same, and then you would add each half reaction together. And that should give you your balanced equation in acidic conditions. Now, if it was basic conditions, as we talked about many times, you basically do all the same steps there. The only difference is at the end, you add, for basic, you add OH minus to both sides equal to the number of H pluses you have in your acidic equation. And the side where there's H plus and OH minus, they combine to make water on that side. The usual then has to reduce down the waters, and you'll be left with, a reaction that is balanced in basic solutions. So we sort of expanded on that. We had a whole couple of labs that involved that, and also lectured on it as well. But again, balancing those more complicated ones involves the water, the half reactions, the electrons, and perhaps the OH minuses if you are doing basic conditions. Now, in addition to sort of that single replacement reactions, there's some other sort of redox reactions that can be classified different ways. There's the synthesis and our combination reaction. And that basically is where you take 2 things and make one, so put it together. The opposite of that is a decomposition reaction, where we take one thing and break it apart into 2 or more things. So for example, if you took your sodium plus your chlorine and make your sodium chloride, This is a combination reaction. It is also a redox reaction. This is 0, 0. This is +1 and -1. So we have a redox reaction happening. If you take water and break it apart into H2 and O2, running electrical current through it. I need a 2 there and a 2 there. Also redox, this is +1, -2, 0, and 0 in terms of oxidation states. So, you know, oxidation reduction reactions happening there. So synthesis, decomposition, single replacement, all redox reactions. A combustion reaction, and in the more generic term of combustion reaction, it really just needs oxygen to be involved. And then technically it's a combustion reaction like magnesium plus oxygen makes a magnesium oxide. This is 0, 0, +2, -2, redox reaction happening, technically called a combustion reaction. Could also, as you see, call it a combination reaction as well. So as we talked about, there is lots of ways you can kind of classify even the same reaction. Most of the time, though, when people think about combustion, they think about the organic combustion. And that is when you take an organic guy, like methane, which is basically carbons, hydrogens, and oxygens, and you react it with O2, you make CO2 and water. So usually when we talk about combustion reaction, that's oftentimes sort of the one that most people sort of think about. But the more really generic version of a combustion reaction, really you just need O2 to be involved in that case. Okay, so we also talked about in terms of redox as well, what is sometimes referred to as a disproportionation reaction. And remember, that is when the same element gets both oxidized and reduced at the same time. So we saw a couple of those examples as well. With our single replacement reactions as well, we also talked about you could get very specific classification of those. You could have a hydrogen displacement like we did, a metal displacement. You know, there's a couple other sort of classifications that we talked about on that as well. We then got into stoichiometry. And remember, stoichiometry really is just using a balanced equation and the mole-to-mole relationship to figure out things. So from this equation, we could say there's 2 moles of A equals BC. That's bad. That's supposed to be a 3B. There we go. Equals 3 moles of B. We could say for every 2 moles of A we throw in there, we get 3 moles of C out. Say for every 3 moles of B, we get 3 moles of C. So for each of these are stoichiometrically equal to each other. So as we talked about, not equal to each other in terms of numbers, but equal to each other in terms of proportion. And we could say, right, 2 conversion factors from each, 2 moles of A over 3 moles of B. Or you could do 3 moles of B over 2 moles of A. And really when we do basic stoichiometry problems, there's really 4 steps. You want to balance the equation. You want to convert whatever they give you into moles. You want to go to the equation and do the mole-to-mole relationship. Then you want to convert those moles into other units. And, you know, so for example, if we were given, we're doing 10 moles of A, how many moles of C would we produce? So we would start with our 10 moles of A. We would go to the equation and find the relationship between A and C, which is this relationship here. We would do our 2 moles of A and our 3 moles of C. And what is that? 30 divided by 2. We'll try it without the calculator, hopefully not too embarrassed. 15 moles of C perhaps would be our amount that we would produce. If we knew what A was, maybe we were given grams of it, we would use the molar mass to get to there. If we knew what the molar mass of C was, we could then convert it to grams of carbon if we knew that by using the molar mass. So very common molar mass kind of used here and also here as well in these type of problems. This is also what is referred to as our theoretical yield, right? So when we produce, how much we produce based off of the equation, that's what's referred to as the theoretical yield. We also talked about that you don't need to go across the arrow. You could stay and do the relationship between these two guys. You could also go from products back that way. You could stay on the product side if there's more than one product doing it. So these sort of basic stoichiometry steps are used to figure out all kinds of things. We can figure out, again, how much product we produce. We could also figure out how much of the other reactant we had. If we had that information, we could figure out how much of another product that we make. Now, when we talked about this, we also talked about the idea of limiting reagents. And limiting reagents are, in every chemical reaction, there's always something that gets used up first. And that reagent that gets used up first is the limiting reagent. And the one that's just left over and you got plenty of is what is known as the excess reagent. And the reason it's important to figure these things out is, as we talked about, the limiting reagent is the one that will determine how much product you produce. How you know it's a limiting reagent problem is, as we talked about, you are given enough information to be able to get to moles of all your reactants. So if you have whatever that information may be, grams of each of them, you could get the moles. We also did stoichiometry to involve solutions. So if you had volume and molarity to get you to moles, you had some other type of units, but enough of that units or information to get you to moles of each of the things that are starting, that is how you would be able to determine which one is that it is a limiting reagent problem. Now, there's a few different ways you could do it. We talked about a couple ways. One common way is just to do two separate stoichiometry problems, one using each of the reactants separately and figuring out how much product each one makes. Whichever one makes the least amount of product would be your limiting reagent, and that also would be your theoretical yield. Another common way is to compare the two reactants and do a quick stoichiometry calculation to figure out, do you have enough of one reactant to use up all the other reactant? And you would do that calculation, compare the starting amounts and see if you have enough. I sort of focused in on ice tables, again, because it'll be beneficial for 200B as well if you take it. But in sort of an ice table approach, you start always with your balanced equation. And in an ice table, we convert whatever they give us into grams. So again, we'll just say we had 4 moles of this guy, 2 moles of this guy, and we would assume we have 0 of this guy. The change would be minus 2x here, minus 3x, and plus 4x. The 2, the 3, and the 4 are the coefficients, and the purpose of that is that will allow you to take into account the correct mole-to-mole relationship. So basically, you will get the right stoichiometry there. If you don't do that, you will not have the right stoichiometry, and you'll end up with the wrong answer. When we get to equilibrium, we would have 4 minus 2, 2 minus 3 in my made-up example here, and 4. This is x, x, and x. Now, what we do is we set these equal to 0. So this would be 4 minus 2x equals 0, which means we get 2x equals 4. We're essentially dividing by 2. We get 2. We'd also set this guy equal to 0. Gives us 3x equals 2, which gives us x is equal to, in this case, what we got there, 0.67, we'll call it. And when you do this, the one that is the smaller number would be your limiting reagent. So by default here, we would know this is our limiting reagent, this is our excess reagent. And the nice thing about this, as we talked about, is that x value is all these x's that are here. So you could relatively quickly figure out C, for example. C would be 4 times x, which means we would take 4 times 0.67 moles. And that would get us 2.67 moles of C was produced. If we knew what the molar mass of C, we could figure out how many grams. That would be our theoretical yield. We could also go back to our limiting reagent, our excess reagent, I'm sorry, and figure out how much of our excess is left over. We would go 4 minus 2 times x, which would be 0.67. And we would have 4 minus 2 times 0.67. 2.66 moles of A that would be left over. Obviously, we put the x into here. We should end up with 0 at that point. And we do very much. So the nice approach with sort of the ice table here was the idea that, you know, you could relatively quickly kind of determine everything that you would need to determine by doing this ice table without having to necessarily go back and kind of start from the beginning and do a whole bunch of, you know, kind of separate calculations. Not that this way is better than any other way. And if you, again, like I said before, if you use the other way, you're perfectly fine. It's all good. You know, it's just a sort of another approach that we talked about there. All right, that led us also to the idea of percent yield. And percent yield is our actual yield divided by our theoretical yield times 100%. And actual yield is usually given to you in a problem. If you're not doing the lab, you would actually get it if you're doing the lab. Theoretical is what you calculate either in a basic stoichiometry problem or a limiting reagent problem. And remember, percent yield, high number is what we're looking for there. So near 100% yield, that's good. Not so much 100% yield, not so good in that particular case. So, all right, let's see here. I think just to give everybody a chance to get up and stretch, we're going to take a 15-minute break. And if you're interested, hopefully, again, this is helpful to you. We'll take a 15-minute break and we'll continue on lecturing or reviewing and stuff like that. Just give everybody a chance to maybe get up and stretch for 15 minutes. So 11:30, we'll come back and we'll continue here. So what I'm going to do is I'm going to actually end the meeting now. And I'll restart it at 11:30. Just come back through the exact same link for lab as you did to get here right now. And we could continue on where we continue on reviewing. But I think I could use a break here to stand. Hopefully you do as well. Okay, so I'll see everybody in about 15 minutes or so, about 11:30, and we'll continue reviewing again. Hopefully this is helpful to you.